When people say there's a 70% chance of rain or that a team has even odds of winning, they are using probability to describe how likely something seems. In everyday conversation, probability is informal. In statistics, however, we make it precise. A probability is a number between 0 and 1 that measures how often we expect an event to occur in the long run. That long-run perspective is essential. Probability is not about what must happen next time. It is about what tends to happen over many repetitions of the same situation. A probability of 0 means the event can never happen. A probability of 1 means it is certain to happen. Values between 0 and 1 describe varying degrees of likelihood. For example, a probability of 0.2 means that in the long run, we expect the event to occur about 20% of the time. A probability of 0.75 means we expect it about 75% of the time. Every probability we compute must lie between 0 and 1 inclusive. That simple constraint is one of the most fundamental rules in all of probability. Probability always begins with an experiment. In this context, an experiment is any repeatable situation whose outcome is not predetermined. Flipping a coin, rolling a die, or drawing a card from a shuffled deck are classic examples. The key features are that the experiment can be repeated under similar conditions, and that we do not know in advance which specific outcome will occur on a given trial. Probability theory gives us a framework for quantifying uncertainty in these repeatable situations. Each time we perform an experiment, we observe an outcome, and the set of all possible outcomes is called the sample space, which we typically denote by the letter, uppercase letter S. For example, when we flip a single fair coin, the sample space is the set containing H for heads and T for tails. When we roll a 6-sided die, the sample space is the set of numbers 1 through 6. Clearly identifying the sample space is essential because every probability we compute is defined relative to that set of possible outcomes. It is important to emphasize that the sample space provides the universe of possibilities. If we do not clearly define S, we cannot meaningfully compute probabilities. Sometimes the sample space is finite, like the 6 faces of a die. Other times it can be infinite, such as all possible real-value temperature measurements. In every case, identifying S keeps us grounded in what outcomes are actually possible before we assign probabilities to events. An event is any subset of the sample space. That means an event can contain one outcome or many outcomes. For example, suppose we roll a die and define the event A as rolling an even number. Then A is the set containing 2, 4, and 6. That event includes 3 outcomes from the full sample space of 6 possible outcomes. Events allow us to group outcomes together in ways that answer meaningful questions, such as whether the roll is even greater than 4 or equal to 1. The probability of an event A is written as P of A. When all outcomes in the sample space are equally likely, we use the classical probability formula. The probability of A equals the number of outcomes in A divided by the number of outcomes in S. This formula works beautifully in settings like fair coins or fair dice, where symmetry makes each outcome equally likely. It gives us a simple way to compute probabilities using counting. Let's apply that formula to our die example. The sample space has 6 outcomes, and the event A of rolling an even number contains 3 outcomes, 2, 4, and 6. So the probability is 3 divided by 6, which equals 0.5. This aligns perfectly with intuition. On a fair die, even and odd numbers are equally likely, so the probability of rolling an even number is 1/2. This is a straightforward illustration of classical probability in action. There are different ways to interpret probability. In the frequentist interpretation, the probability of an event is defined as the long-run relative frequency of that event. That means if we repeat the experiment many times under identical conditions, the proportion of times the event occurs will approach the probability. For example, the probability of flipping a head on a fair coin is 0.5 because in the long run, about half of all flips will show heads. This long-run perspective is foundational for statistical inference. Now let's consider example 1, rolling a six-sided die. The theoretical probability of rolling a 6 on a fair die is 1 out of 6, which is approximately 0.167. That number comes directly from the classical formula. There is one favorable outcome out of 6 equally likely outcomes. This theoretical value represents what we expect in the long run, not necessarily what will happen in a small number of rolls. Suppose we actually roll the die 20 times. Because 20 is a relatively small sample, the number of 6s we observe may not match the theoretical proportion exactly. For instance, we might roll a 6 only 2 times out of 20. The relative frequency in that case would be 2 divided by 20, which equals 0.1. That is noticeably different from 0.167. Small samples can fluctuate quite a bit due to randomness. If we look at a bar chart of the 20 rolls, we may see noticeable imbalance. Some values might appear more often than others simply by chance. This unevenness does not contradict the theoretical probability of 1/6. It simply reflects the natural variability that occurs in small samples. Probability describes long-run behavior, not short-run perfection. Now suppose we roll the die 1,000 times. With many more trials, the counts of each face will tend to become more even. The relative frequency of rolling a 6 will likely be much closer to 1 divided by 6, or approximately 0.167. The bar chart for 1,000 rolls will typically look far more balanced than the chart for 20 rolls. Increasing the number of trials reduces the impact of random fluctuation. If we increase the number of rolls even further, to 1 million for example, the relative frequencies of all outcomes will be extremely close to their theoretical values. Each face will occur at roughly 1/6 of the total rolls. This illustrates the central idea behind the frequentist interpretation. As the number of repetitions grows large, the observed proportions converge toward the true probabilities. Example 2 involves flipping a coin many times and tracking the cumulative proportion of heads. Early in the sequence, the proportion of heads can jump around dramatically. After just a few flips, the proportion might be 0.2 or 0.8. But as the number of flips increase, the cumulative proportion tends to stabilize near 0.5. The graph of the cumulative proportion typically shows large early swings that gradually dampen as more flips are added. This behavior is explained by the law of large numbers. In 1689, Jacob Bernoulli proved that as the number of independent trials increases, the relative frequency of an outcome approaches a fixed number in the long run. That fixed number is the true probability. The key assumption is independence. The outcome of one trial does not affect the outcome of another. Under that condition, the long-run proportion converges toward the probability. The law of large numbers provides the theoretical foundation for the frequentist interpretation of probability. When we say that the probability of rolling a 6 is 1/6, we mean that if we roll the die many times, the proportion of 6s will approach 1/6. In symbolic form, as the number of trials increases, the relative frequency approaches P of A. This idea connects mathematical probability to observable data. Finally, it is important to note that probability can also be interpreted subjectively. In the subjective interpretation, probability represents a personal belief about how likely an event is based on available information. Two individuals might assign different probabilities to the same event if they have different knowledge or perspectives. Even under different interpretations, however, probability values must still lie between 0 and 1 and must obey the same algebraic rules. No matter how we interpret probability, the mathematical structure remains consistent.